Okay, so we spent the first 10 minutes or so here just having people fill in as much of the Cayley table for D3 as they can, D3 being the symmetries of an equilateral triangle. As a set, this group has 6 elements in it. The R's are rotations, although R0 we're only informally thinking of as a rotation. I mean, it keeps things fixed. You could think of that as a fixed reflection as, if you want as well. It's just the identity mapping that maps every point to itself. R120 rotates counterclockwise by 120 degrees. R240 rotates counterclockwise by 240 degrees. The net effect of which could also be obtained by rotating clockwise by 120 degrees, but we think of it in terms of counterclockwise rotations. V is a reflection across the vertical line of symmetry. D is a reflection across that diagonal line of symmetry. And D prime is a reflection across this diagonal line of symmetry, pretending this is an equilateral triangle, pretending that the picture is perfect. When you start filling out the Cayley table, you can do a lot of it fairly quickly. In fact, everything that I haven't read, I did very, very quickly. R0 is the identity. It's the identity mapping function. It is also the identity with respect to function composition. When you compose R0 with anything, you get that anything back, whether you do it on the left with R0 composed with R20, for example, or whether you do it on the right with R120 composed with R0. You can fill those in really quickly. These expressions in the middle are easy to figure out as well. It's clear that 2 rotations that are composed will give you another rotation. When you rotate by 120 degrees counterclockwise twice, you get 240-degree rotation. When you rotate counterclockwise by 240 degrees twice, that's equivalent to 480 degrees. Mod 360 degrees, you might say that's the same as 120. And when you compose R120 with R240, you do a 360-degree rotation, which is equivalent to not moving at all. That's the net effect. It's the same as R0. Yeah, that can be figured out pretty quickly. Then the fact that each reflection is its own inverse, right? When you compose a reflection with itself, V squared, for example, is getting you back to the original configuration. It's the identity. It's the same as R0. Same thing with the other reflections. All right, everything that's going to be in purple takes longer to figure out. You could draw diagrams like this and not bother drawing the triangle. Just keep track of the numbers or the colors. If you were going to color the vertices, for example. So this was my numbering. I started with the 1 in the lower right corner, 2, 3 going counterclockwise. You can number it other ways. V reflects across the vertical, so the 1 and the 3 get swapped. It's a permutation of the symbols 1, 2, 3. The 1 and 3 get swapped and the 2 stays fixed. Then D swaps the numbers lower left and the top. The 1 and the 2 here get swapped, leaving you with this particular configuration. And comparing that with the original configuration, you can go from here to here by a rotation by 120 degrees. Remember to get the order right. DV, where I have D on the left and V on the right, means apply V first because of function notation. That's probably the most common mistake here that people make, is forgetting, okay, this means I need to apply V first, then D, because with function composition, you work from right to left. So the net effect is R120. You can put that there. DV, the one that's on the left, you get from the column here. The one that's on the right, you get from the row up there. So DV goes right there. Same row as D, same column as V. But again, it means do V first, then D. R120V would mean do V first and then rotate by 120 degrees. You'd end up with this configuration. To get from here to here at the start, it's sufficient to swap the 2 and the 3 get swapped. So that's the same as a reflection across the diagonal from upper left to lower right in the original picture. And to get to figure this out, you'd want to do R120 first, then V. It's different. Therefore, this group is not, what's the word? Not Abelian. You could also say not commutative, but it's more traditional to say not Abelian. if there's at least two elements that do not commute, here are two elements that do not commute, R120 and V. When you do them in opposite orders, you get different answers. Okay, so this matrix, this 6x6 matrix in the main body of the table is not symmetric. If it were, these two things would be the same, but they're different. Now, maybe you figured this out already. How is trying to fill out the rest of the table made easier in some ways, in a way that's maybe similar to Sudoku? Did you figure this out when you've tried Cayley tables or looked at them before? Well, for one thing, well, this is not the Sudoku-like thing, exactly, at least. For one thing, the composition of two reflections has to be a rotation. So you know down here in this lower right corner, this box of 3x3 entries, you have to have all rotations. And here's the Sudoku-like part. What would have to go there? R240, right? Because you can't have one of these repeating in the same column because you'd end up violating the cancellation law like we talked about the other day. That's got to be R240. I mean, you can check it by doing D first, then V. Oops, D prime first, then V. And then you can continue like Sudoku. This has got to be an R120 here. This has got to be an R240. Each thing has to occur once. This has got to be an R240. And this has got to be an R120. That will continue. That kind of game can be continued in these spots as well, but we'd have to figure out some more things to be able to fill it in more. We don't have enough information at the moment. Before we fill this in, I want to go back to thinking about these as permutations like we talked about the other day, class 4. And I'd also like to introduce a special notation to you. Here again is the original labeling, 1, 2, 3. This is called cycle notation. For permutations. In this case, on the set with 3 elements, 1, 2, 3, which the other day on Monday I called C3. I called it C3 on just the spur of the moment. I don't know that there's a better letter to use or a worse letter. It's not a standard letter to use as the C here. C3 is not a group. It's just a set. Just a set with 3 elements. I happen to be labeling those elements with numbers 1, 2, 3, but they could have been labeled with other things. Letters A, B, C, colors red, blue, green. The labels are not important. What's important here with this set is that it's got 3 elements. It's just convenient to use the numbers 1, 2, 3. But again, this is not a group. I'm not defining an operation on this. Maybe I could make it. Yes, I certainly could make it a group if I wanted to define a certain operation on it. Though it would, to be a group, the operation wouldn't necessarily correspond to anything natural. What I'm using with this notation, again, this is called cycle notation, is it's supposed to represent functions that permute this set of three things, 3 objects. The 1 by itself here, I don't know if that's the best notation. That's supposed to emphasize that 1 gets mapped to itself. It also really means, since 2 and 3 are not shown, it means 2 gets mapped to itself and 3 gets mapped to itself. In other words, this is the identity. permutation. I could also write those things as alternative notations for this identity function that maps every one of these three elements to itself. And when I say R0 equals that, I'm being hand wavy. R0 is really a transformation of the plane that sends all points in the plane to themselves in reality. But as far as its effect on the vertices of the equilateral triangle, it keeps those vertices fixed. I could think of the elements of this as corresponding to the vertices. And that's really what I'm doing. And the 1, 2, and 3 are just labels for the vertices. This notation, 1, 2, 3 in parentheses like this, no comma between these, by the way, represents a permutation that, watch what I do here, maps 1 to 2, 2 to 3, and then maps 3 back to 1. That's the way you want to think about this. So, and that's the effect of R120, the rotation, the counterclockwise rotation by 120 degrees on the vertices of the triangle. 1 gets mapped to the position where 2 was, 2 gets mapped to the position where 3 was, and 3 gets mapped to the position where 1 is. That's why I'm saying R120 equals this. When you use this notation, you're really thinking of it as a permutation on this set of 3 objects, on the vertices if you prefer. R120 really is a rotation of the plane. So again, I'm being hand wavy here. It's not that these are literally equal to each other, but it's just sort of a way to represent them. R240 maps 1 to 3, 3 to 2, and 2 back to 1. Think about it here. Go 240 degrees. 1 gets mapped to the location of 3. 2 gets mapped to the location, or 3 gets mapped to the location where 2 was. And 2 gets mapped to the location where 1 was. V, I'm writing this way. 1 gets mapped to 3. 3 gets mapped back to 1. And evidently, since 2 is not in there, 2 stays fixed. And that's what happens under a vertical flip. 1 and 3 get swapped, 2 stays fixed. Here, for D, 2 gets mapped to 3, and then 3 gets mapped back to 2. D is a reflection across that diagonal. Yeah, 2 and 3 are swapped, 1 stays fixed. And then D prime, 1 gets mapped to 2, 2 gets mapped back to 1, and 3 stays fixed. When you write these things in cycle notation, and then you compose these functions, it's a convenient way of doing your calculations, and you don't have to make pictures. For example, if you want to now calculate, say, R120 composed with D, R120 composed with D, we're representing R120 with this cycle, 1, 2, 3. We're representing D with this cycle, 2, 3. What's the answer? Remember, this is still function composition. So overall, you have to go from right to left. This function, this symbol represents a function that maps 2 to 3. But then when you plug 3 into this function, it maps 3 to 1. So ultimately, under the composition, 2 gets mapped to what? 1. What does 1 get mapped to? Well, under this one, it gets mapped to itself. 1 gets mapped to 1, but then 1 gets mapped to 2 as I move to the left. Ultimately, 1 goes back to 2. What does 3 get mapped to? Under this function, it gets mapped to 2. But then you got to plug it into this function, and it gets mapped back to 3. 3 gets mapped to itself. So the answer is this, but wait a minute, that's not in this list anywhere. Or is it? It's that one. Cycle notation is not unique. This is the same thing. Because both of these symbols represent 1 getting mapped to 2 and 2 getting mapped to 1 and 3 staying fixed. So this is D prime. R120D is d prime coming back here. I could fill in a d prime here. Now thinking about the Sudoku, it's got to be v there. Continuing. I guess it looks like to be, well, okay, we'd have to be a d prime here looking at the column. It would have to be a v here looking at that column. And it'd have to be a d there. So just figuring out that one more composition allowed me to fill in the rest. Let's try filling in this. Let's try doing dr120 with this cycle notation. dr120. D is 2, 3. R120 is 1, 2, 3. Compose from right to left. What does 1 get mapped to? Well, under this function, it gets mapped to 2. Then you plug 2 into this function, and it gets mapped to 3. So ultimately, 1 gets mapped to 3. Does 3 get mapped to 1? It probably does, right? Because this has got to be another reflection. Check it. Under this function on the right, 3 gets mapped to 1. Plug that into this function, 1 gets mapped to itself. Because you don't see a 1 in there. Ultimately, 3 does get mapped to 1. Does 2 get mapped to itself? Yes, because first it gets mapped to 3, but then 3 gets mapped back to 2. And this is V. What we're doing with this cycle notation is we're introducing the idea of a permutation group pretty early here as we're working on chapters 1 and 2. In the book, they don't get to it until chapter 5. But it's a hard enough, chapter 5 is a hard enough chapter that I think it's good to introduce permutations early to get warmed up toward it. So dr120 is V. I guess that means this has to be D, which now going across these ways, this would have to be V, this would have to be D prime, and this would have to be D. Okay, so yeah, you can do it with pictures and you don't need to draw the triangle. Effectively, I'm thinking of it in terms of permutations there, though the permutations are visual in terms of locations of things. Or you can use this cycle notation for the permutations. Though I am really abusing notation here. That's the best way to describe this is abuse of notation. Because these really represent transformations of the plane, whereas these symbols really represent transformations of this set of this finite set. Functions that are one-to-one and onto are permutations on a finite set. But you get the idea. It's a natural thing to do. Let's think about this some more. We've seen it's non-Abelian. It is a group. As far as certainly it's closed under composition. The operation again is composition. Certainly associativity works, and the reason, if you had to give a reason, is you'd say, well, we already know function composition by definition is associative. And that really is true. Maybe it's worth writing out in an equation here. Let's just imagine our functions as being f, g, and h. And I'm going to go ahead and use the circle symbol for function composition. Actually, we kind of already talked about this to some degree when you had that first homework problem where in class we talked about verifying associativity, though when you did it by hand on your own, you didn't actually have to verify that part. Just by definition of what does this mean is essentially why it works. When I put the parentheses like this, by definition, that means this. Because, go back over here to using alpha and beta as function names. got something like that. By definition, that's alpha of beta of x. Plug beta of x into alpha. Here I'm thinking, when I got the parentheses like this, I'm thinking of this as being a single function, f circle g. So by this definition, this would equal that. But there I have the circle again. By definition, this would equal this. Plug h of x into g, like that, and then plug that quantity into f. On the other hand, if you use your parentheses like this, with them being around the g compose h instead, by definition, you'd initially think of it this way. But then again, by definition, you'd expand this thing inside the input for f as g of h of x. And ultimately, these two things match. So it's just by what function composition means. I'm going ahead and using the circle notation here for the function composition, though our textbook doesn't typically bother with that, to verify associativity. So function composition is always associative. There are binary operations that are not associative, but they're weird, typically. So all the examples we consider, well, I mean, okay, they're not always weird. Subtraction is a binary operation that's not associative. That might be a little confusing since subtraction can be defined in terms of addition. So for example, 10 minus 3 minus 1, putting the parentheses that way, is 7 minus 1 is 6. But putting the parentheses the other way gives you 10 minus 2, which is 8. So yes, subtraction is not associative. How does that work if addition is associative and if subtraction can be defined in terms of addition? Well, if you define these things in terms of addition, you're not really doing the same additions. That's the point. This is the same as, in terms of addition, it's the same as 10 plus negative 3, then plus negative 1. But this is actually a different addition. As an addition, it's really 10 plus negative of 3 plus negative 1, which I guess you could write as 10 plus negative 3 plus 1. This is ultimately 10 plus negative 3 plus negative 1. This is ultimately 10 plus negative 3 plus positive 1. They're really different additions if you think of them in terms of addition. Does that look right? No mistakes there? So this is not contradicting the fact that addition is associative. There's an identity R0, and every element does have an inverse. For example, the inverse of R240 is R120, and vice versa. And here, when I use the inverse symbol, it does not technically mean an inverse with respect to a literal multiplication. It's really an inverse function, right? Because the operation's function composition. But in a sense, in the abstract, we're pretending it's a multiplication as far as an abstract group, you might say. And for each one of the reflections, they are their own inverses. And of course, the identity is its own inverse too. And the group is not abelian. Some new terminology here. This is now chapter 3 terminology that I'm about to introduce you to. The order of a group is the number of elements in the group. So the order of this group is, go ahead, 6. And we use the following notation, in our book at least. We put absolute value signs around the group to denote its order. Now, should you say absolute value of D3? No. Say order of D3. And it doesn't mean order as in putting something in an order. It means the size, so to speak. It means the number of elements, in this case, 6. The order of Dn, symmetries of a regular n-gon, is 2 times n. Because you got n rotations and n reflections. This is not a unique notation. Other books use like a little O to represent order. Other textbooks. But as far as I know, those are the 2 most common notations. This is not a 0 there. It's a little O. Maybe you want to make it cursive or something to emphasize it's a little O. O for order. That's what our book does. That's the order of a group. Some groups are infinite. For example, the group of integers under addition, order of Z, is infinite. Does that mean we should write equals infinity? Well, I just did. I just wrote equals infinity. Should I have? It's forgivable in this context. Not that infinity is a number for us. Actually, in some math classes, infinity is a number. And instead of saying this is just infinity, they'd say it's got a cardinality of something called aleph naught. Has anybody ever heard of that before? I don't know if I can draw it though. Sort of a fancy looking N kind of shape. It's actually a Hebrew letter, aleph. Aleph naught. It stands for what's called countable infinity. Have you heard of countable infinity versus uncountable? If you've ever TA'd people in creative problem solving, you may have heard them, seen them learning about different kinds of infinity. The integers is a countably infinite set. I'm not going to define what that means today, at least. As opposed to the real numbers under addition is a group. You might say that equals infinity as well. However, the cardinality of that infinity is actually not aleph naught. It's called C for continuum. How do I explain this in a short amount of time? It's a bigger size of infinity, which makes some intuitive sense because there's plenty more real numbers, it seems, than there are. There's infinitely more real numbers, you might say, than there are integers, but that's not a proof. You have to define exactly what you mean by cardinality. It's defined in terms of one-to-one and onto functions, actually, if you are interested in looking it up. It's actually not super hard to explain. But it is a bigger size of infinity. So I'm being hand-wavy here when I write these things, these equations. the way our book approaches this is it doesn't make a distinction between these. It just says these groups have infinite order. That's all it says. Something called the continuum hypothesis was a hypothesis written down by a person named Cantor back 130, 40, 50 years ago or so, that there's no size of infinity in between these. And Cantor, you might say he went crazy trying to prove it and also trying to disprove it, because he thought it was true at first, but then he was never able to prove it. So then he thought maybe it's false. So then he tried to disprove it, but he kind of went crazy. He did end up in an institution. Kind of a sad story, but it turns out his attempts were futile, because later on, after he died, people proved you can't prove there's no cardinality between these, and you also can't disprove it. Somebody proved you can't prove there's one between, and you can't disprove it. Or I guess I should have phrased that: you can't prove that there's not one in between, and you can't disprove it. It's outside the standard axioms of arithmetic, is what that really means. And so there's a reason Cantor failed, is because it's not provable and not disprovable. Pretty strange thing. Anyway, that's outside the scope of our course, but I thought it would be worthwhile to just mention it. Okay. You can also define what's called the order of an element. What's the order of an element? Given a group, capital G, the group itself could be finite, it could be infinite. And an element, call it little g in capital G. The order of G is written with the same kind of absolute value notation. But again, don't say absolute value of G, say order of G. That doesn't mean we won't ever use the actual ordinary absolute value in here sometimes. That could be used, so you have to tell from context whether I mean order or absolute value. And you can define this in a piecewise way. It equals a finite number n if n is the smallest integer, smallest positive integer, such that, I'll abbreviate ST, G to the n is the identity, n equals infinity if there is no such n. And this infinity happens to always be the aleph not infinity. Though you don't need to know that. It's just an extra side comment. And the alternative notation for this is little o of G. There, I made it slightly cursive. Just to emphasize it's not a zero. It's a little o. But our book uses this notation. So thinking about D3, well, I guess you can look at your Cayley table. What's the order of R120 in D3? What's the smallest positive power, so to speak, under function composition that you can raise R120 to get back to the identity R0? It'd be 3, yep. R120 squared means R120 composed with itself is R240. R120 cubed is R120 composed with R120 composed with R120. 3 rotations counterclockwise by 120 degrees gives you a 360-degree rotation back to R0. This got an order of 3. It's the same as the order of R240, actually. They both have order 3. What about the order of any reflection? These are the same, and what are their orders? 2. And then the trivial case is always the order of the identity. In any group, no matter what group it is, the identity would have order 1. The identity to the first power does equal itself. Note that all these numbers, 3, 2, and 1, they all divide the order of the group, 6. These all divide, as in the divide symbol, the order of D3, which is 6. That always has to be the case if your group has finite order, at least, if it's a finite group. When a group has finite order, you call it a finite group. If it's got infinite order, you can call it an infinite group. If your group has finite order, the order of any element has to divide the order of the group. Could it ever equal the order of the group? What do you think? Could the order of an element ever equal the order of the group? Maybe think about one of the Z examples. Zn for some n. Like say in let's keep it simple, say in Z3, when 3 is prime, definitely, I mean, the only numbers that divide 3 are 1 and 3, only positive integers. The order of an element is either got to be 1 or 3, and if it's not the identity element, it can't be 1. In Z3, remember, this is an additive group. Instead of saying G to the n equals E, you'd really be thinking of n times G equaling 0, you might say, instead of E. Where n times G really means G added to itself n times. N doesn't necessarily have to be an element of the group. The order of 0 here is 1. The order of both 1 and 2 is what? Three. Isn't it great? You get to write crazy looking equations like these. Isn't this class great? The order of Z3 itself is 3. Yes, 1 and 3 both divide 3. Why is the order of 1 equal to 3? You're not thinking in terms of powers here. You're thinking in terms of multiples. 1 times 1 really means just 1 added to itself once, so to speak, which means it's just itself. 2 times 1 doesn't mean a literal times in a group. It means 1 added to itself twice. Which is 2, which is not 0. These are both not the identity yet. 3 times 1 means 1 added to itself 3 times. That is 0 mod 3. You're back to the identity. The operation's addition, so you gotta be careful about what the operation is. We're not doing powers of these elements, we're doing multiples, meaning we are adding them to themselves a certain number of times. With 2, 1 times 2 is 2. 2 times 2 is 2 plus 2. Mod 3 is 1. Three times 2 is 2 plus 2 plus 2 is 6. Is 0 mod 3. I'm being a little sloppy with where I put the mods and not really worrying about that too much. Just putting the mod at the end, so to speak. These calculations confirm the fact that these orders are both 3. And so yes, the order of an element can be equal to the order of the group. Z has infinitely many elements. It's got infinite order. And yes, I'll be okay with you using this shorthand, equals infinity, though our book doesn't typically do that. It typically just says the order of Z is infinite. But I'll be okay with that as a shorthand. What are the order of its elements? Well, the order of 0 is 1. If A in Z is non-zero, what is the order of A? You keep adding A to itself, are you ever going to get ignore that. Are you ever going to get back to 0? No, you're not. It's infinite. Why did more notifications come? 2 notifications come at once. I guess that makes sense. Z is infinite order, so wouldn't all of its non-identity elements have to be infinite order? You might think that that could be a conjecture that might be true. If a group has infinite order, all of its non-identity elements would have to have infinite order. But that's actually false. And we've actually seen an example that when if you think about it in a bigger context, you'll see that it's false. Well, here's a simple example. That's not what I was initially thinking of. Take the real numbers under multiplication. That's actually not a group, as I just stated it there, because 0 doesn't have a multiplicative inverse. However, if you take out that rascal 0 and call the resulting sets R star, say, means R take away 0. Have you seen that kind of notation before? Set difference. Some people use that kind of notation for it. Take all the real numbers as a set and take away one element. In this case, the element 0. This is the set of all real numbers that are non-zero. This actually is a group under multiplication. Now all the elements in this do have multiplicative inverses because you're not including 0. However, even and its order is infinite. However, there is a non-identity element in this group that's got finite order. Certainly the identity 1 has finite order, and its order is 1. But there's another element besides 1 that's got finite order. What would that other element be? There's just one other element that does. Operations multiplication, not addition. Go ahead.
-1.
-1, yeah. -1 is not the identity, but -1 squared is +1 is the identity. The order of -1 is 2. So the conjecture that a group of infinite order, all its elements, all its non-identity elements have infinite order, that as a conjecture is a false conjecture. And here's an example that illustrates that it's false. Let me go even wilder here. C star stands for the complex numbers take away 0. This is a group under multiplication. One is an element of C star, and it is the identity, and its order is 1. And C star does have infinite order. I claim that this group C star that has infinite order has finite subgroups of every possible order. Meaning it's got a subgroup of order 1, just 1 by itself. I claim it's got a subgroup of order 2. I'll even tell you what it is. The 2 element set, 1 and -1 forms a group under multiplication, a group of order 2. That's also a part of a subgroup of this one as well. The other day, I don't know if it was Monday or last Friday, we did talk about an example of group with order 4 that involved complex numbers. Do you remember what it was? Guess it was Monday. We did it. 1, -1, I, -I, yeah. That's a subgroup of, that was under multiplication. That's a subgroup of C star. Subgroup meaning subset, and also the operation is the same. 1, -1, I, -I is a subgroup where the subgroup has order 4. And also, 2 elements in that subgroup have order 4. I and -I have order 4. Right? I to the first is I, not equal to 1. I squared is -1, not equal to 1. I cubed is -I, not equal to 1. But I to the 4th is 1. The elements I and -I have order 4, and that also, this is a subgroup generated by I or -I. All these things are powers of I and also powers of -I. And this subgroup of C star has order 4. Subgroup, again, meaning both a subset and a group under the same operation. It's analogous to subspace in linear algebra. I just claimed 2 minutes ago that this group has finite subgroups of every order and elements with every possible finite order. Who feels like maybe they know enough about complex numbers to identify an element of order 3? Maybe you do, maybe you don't. Has anybody learned enough about complex numbers? Yeah, we do teach complex analysis here, though it's not every time we teach topics in math. I've taught complex analysis, so has Professor Auk. So we don't always get people who are knowledgeable about complex numbers coming through the curriculum here. So I imagine this being something called the complex plane. This is called the real axis. This is called the imaginary axis. But the imaginary axis, I did draw it. It is there. Okay. It's not just a figment of your imagination. An arbitrary complex number corresponds to a point in the complex plane. The part that doesn't involve an I is a real number corresponding to the first coordinate of this point. And the part that is next to the I, the B here, is a real number corresponding to the second coordinate of this point. Because it's next to the I, we call it the imaginary part of the complex number. Without explaining what's going on here with complex number multiplication, complex number multiplication has beautiful geometric interpretations. I'd highly suggest you learning about it. You can relate complex number multiplication to polar coordinates in a very nice way. And if you consider the unit circle centered at the origin here of radius 1, it turns out whenever you multiply two numbers on the unit circle in the complex plane, you'll stay on the unit circle of radius 1 centered at the origin. And what that means, one thing that means is the unit circle itself is an infinite subgroup of C star. All these complex numbers on the unit circle form a subgroup of C star under multiplication. That's an infinite subgroup because there's infinitely many points in the circle. And the finite subgroups of C star are all on the unit circle. Yeah, 1 and -1 are. So are I and -I. There's your subgroup of order 4 right there. Subgroup of order 3, out of colors, turns out to include 1. It's got to include 1 still. And also a number right about there and a number right about, oh, this is not drawn very well. Right about around there. 1 at 120 degrees. And 1 at 240 degrees. And using polar coordinates, you can figure out what those numbers are. The 1 at 120 degrees is cosine 120 degrees plus I sine 120 degrees. Cosine of 120 degrees is -1/2. Sine of 120 degrees is square root of 3/2. That complex number under multiplication has order 3. Its absolute value is not 3. Its order as a group element is 3. Its distance to the origin is still 1. You might say its absolute value is 1. And let's just end class by verifying that on Mathematica here. -1/2 plus I is a capital I in Mathematica times square root of 3/2. I square that, and expand it, I get negative 1/2 minus I squared root of 3 over 2. That's the one that I drew down there. If I cube it and expand it, I get 1. Try confirming that by hand if you wanted to. Okay, it does work. So C star again is an example of an infinite group under multiplication here. Complex numbers except 0. Take away 0. Don't include it. It's got subgroups of every order. Subgroup order 7 would consist of 7 elements along the unit circle, including 1, that are all an angle of 360 degrees divided by 7 from each other, etc. Okay. All right. Have a good day.